Hey, I'm not the electrical guy. I'm a metallurgist. Don't ask me about that. I have no idea about electricity. Do you know that feeling that sometimes you need information outside your core field? I often do that, and one of the reasons why I make this podcast is that I also want to learn for myself to become broader in my knowledge. So therefore, I am often asking people who are outside my comfort zone to tell me about what they do so I learn more. Today, in this episode, I have invited a lady who is a motor designer and electrical background, and her ideas about material was not very good. So I challenged her to learn more about materials that I use in motors, because she realized that a lot of opportunities are there if you're aware of how you can manipulate the materials and optimize your motor, both on the geometry, on the electrical side, and on the materials. So this episode is with Ruchika. She had not a big background about materials, but I have challenged her. I also added in with my own knowledge about some of the materials. And I would love you to see this episode, because the learning curve of Ruchika in this is extremely steep. And if you are a motor designer or you have colleagues who are working with motor materials, please take a look at this, because I would love some feedback. We have some materials that we really don't know what are the applications, and we would love you to give input in the notes below on this YouTube podcast. Enjoy it, and hopefully you will have a steep learning curve as well. Yeah. Hi, Ruchika.
Hi, Peter. Nice to see you.
You too. Welcome to the podcast Everyday Metallurgy, where today we're going to talk about materials in electrical motors. Uh,
Yes.
yeah, electrical motors is hot, because everybody, at least in the part of the world where I am, want an electrical car, and the drivetrain is an electrical motor.
Yes.
So there's a heavy run on laminated sheet, but are there alternative materials? And I have invited you to talk about that, because we'll dig a little deeper into what are possibilities when you want to build a stator in such a motor. Uh, but first, would you give an introduction to yourself, your background, and what you're doing today?
Okay. First of all, thank you so much, Peter, for having me on your podcast channel. And I must tell you that this is my very first podcast ever, and it happened to be on your channel. So I'm so happy about that. So I'm a little excited too. So just forgive me if there are any mistakes because I don't know how to deliver on podcast. So I'll try
It's
my
no
best.
problem. Yeah.
So I'm Ruchika Singh, and I'm based in Denmark. And I'm a motor design engineer by profession. I've been designing motor for 5.5 years for different applications like high-speed flywheel applications and fan applications in my recent job. And my thesis, where I actually designed motor for electric Formula car, was a hub
Hmm.
motor. All these motors have been radial flux designs. So I've only been doing radial flux design, and prior to, so I came to Denmark to do my master's in Technical University of Denmark. And you may ask why Denmark. I actually always wanted to study at DTU.
Hmm.
I was really happy to be a part of that. And DTU actually gave me a lot of things. I think most of the things I am today is because of that university. And I'm happy to be called a DTU alumni. I came
Hmm.
from India,
Yeah.
and I finished my bachelor's degree in electrical engineering there. And after that, I started working a little bit in power electronics uh, division. So basically, all the inverters and power electronic devices control algorithms for motors, and that's how actually I realized that now I have talked to the motor enough. I want to get inside the motor and design one. So that's
Yeah.
why I actually came to Denmark and did my master's and specialized in motor design.
Mm.
And currently, I'm looking for opportunities to apply these skills for my next role in electric motor design and development. And while I'm doing this, I started writing my LinkedIn newsletter, Mind Your Motors, because I always wanted to do one. Because as
Mm.
engineers, we always design and keep things in our notebook and forget about it. And I thought, okay, I just don't want my notes to be limited in a notebook. I'll just put it on the internet for other people,
Yeah.
and people can interact with my articles, and I get to learn more and
Mm.
hear feedback from them, so I can learn more and better from this platform. Of course, I'm no expert. I have a lot of things to do. I also realized while I was preparing for this podcast that I have so many things to learn. And I'm so happy that I'm here on this podcast, because also, like, it's also a very strong, or I think it's a very good thing to be on this podcast, because when you are a motor design engineer, you deal with a lot of materials for your motor, but you don't actually look into the metallurgical part, because
Mm.
you don't have the time basically, and you
Mm.
don't probably feel the need, but
Yeah.
it's very important to understand what addition to that metal will behave, or how will the
Mm.
metal behave because of that material
Yeah.
added to that, and how
Mm.
does that affect the properties. So I
Yeah.
think I'm going to learn a lot on this episode. I'm looking forward to it.
Yeah. Or some motor designers, they just think, I don't need to know about the metallurgy because I can call Peter.
Okay, that's also a good option.
Yeah, but no, it would be great to if we could spread out the words about the materials in motors. And I'm a fan of your blog, Mind Your Motor, and
Thank you so
I'm a
much.
follower, and I'm also learning a lot from reading what you do
Oh,
there. So
thank you
thank
so
you
much,
for
Peter.
posting. Yeah.
Thank you very much for reading.
Yeah. Should we start talking about what parameters are important when we look into the materials for a stator?
Yes,
Can
yes.
you give some point on that?
Yeah, I'll share my presentation so we can actually look at some of the points we have.
Hmm.
So, some of the parameters we actually look at when we start to select materials for the core of the motor. So, basically, we are talking about the stator, motor
Mm.
stator here, and stator has two parts, the windings, and the windings go on to the core of the motors.
Yeah.
So, we are talking about core to begin with, and what parameters would you like to have? Uh, so, first is high permeability.
Mm.
They should have low core losses. They should have high magnetic saturation. And then you also laminate steel, and there's a reason why you laminate. So we'll also discuss about that.
Mm.
And why should electrical steel have thinner hysteresis loop? Because if you compare
Mm.
them with magnets, magnet have a thicker one, and the electrical steel has a thinner
Mm.
magnetic or hysteresis loop. So we'll also
Mm.
discuss about that.
Yeah.
So
Yeah.
the next slide, the permeability. So
Mm.
basically, uh, what is permeability by definition? So it's a property of a magnetic material to carry the flux as efficiently it can and to convert it into better output. And we want that material, any material, to have a high permeability so that it can efficiently carry the flux. So we are looking for materials which have that property.
Mm.
And then you also want to minimize core losses. Now, core losses has two components: eddy current losses and hysteresis losses. Eddy current losses are basically due to the eddy currents induced into the material itself uh, by changing magnetic flux,
Mm.
and that loss is giving rise to eddy current losses. And hysteresis loss itself is when the magnetic domains of the material align and realign when the
Mm.
flux is changing path. So
Yeah.
that's what is giving rise to eddy current losses, and you
Mm.
want both of these to be as minimum as possible.
Yeah. So if you have a permanent magnet, you could say you have a very high coercivity. So the
Yes.
the the force to be unmagnetized is very high, so you need to put a lot of energy to demagnetize
Yes.
it. But here you
Yes.
want a very small coercivity because you
Yeah.
don't want any losses when you change the
No.
field.
No, no, that's exactly what we are actually trying to see in a material, because in a magnet, you want them to retain the magnetic flux density. So if you apply, or if it had a lower coercivity, then it would be very easy to demagnetize it. And we don't want that in a in a
Mm,
permanent magnet machine. But whereas in an electrical steel, you don't want them to hold that magnetic flux, because you want them to be want them to be
mm,
changing faster. So magnetize in one direction and then magnetize in the other direction.
mm,
So that's why the force required to magnetize and demagnetize an electrical steel should be small. So small coercive force compared
yeah,
to a hard ferromagnetic material, which is a magnet
mm,
in this case.
mhm, yeah,
Yeah, so and also this area under this loop, it's quite thin. If you see the hysteresis curve on the left side,
mm,
and we want that to have as thin as possible, and because we want to have lower hysteresis losses, and you do something to make that thinner. We'll also talk about that. That's why exactly what electrical steel is made
mm,
for, and why they have thin hysteresis loop. We'll also talk about that.
mm,
And eddy currents, basically, I also talked about when you have this change in magnetic field in the material, you have eddy currents induced in the material. So if you see the picture on the left side, this is a very simple comparison I got from the internet. So if
mhm,
you see you have a block of material, just a thick block of material, and you see the path of the eddy currents, they're quite long.
mhm,
And if you see on the right side, there's something, the block is now cut into small sheets.
mhm,
And why you do that is basically you're trying to make this eddy current loop smaller. And when you make these eddy current loops smaller, you actually reduce the eddy current losses. So you're making the path shorter, and so you reduce the eddy current losses. So
mm,
this process is called lamination. And that's why you use
yeah,
laminated electrical steel in
mm,
electric motors to reduce eddy current losses further.
yeah,
Yeah.
mm.
Then, yes. Okay.
Uh,
Yes.
yeah. Are there other parameters important for such a soft magnetic material?
Yes. So, for example, high magnetic saturation. So, when I talk about high magnetic
Mm,
saturation, I'm talking about higher value of flux density. So, I
yeah,
want that value on the BH curve to be
mm,
as high as I can get.
yeah,
And you may ask why. So in a motor, all you want is to have a better torque performance. So it's a combination of two parameters: the flux density you can get in the air gap of the machine, and the current you can push through the windings. And the combination of these two gives you the torque. So you always optimize for these two parameters, not all, not mainly only these two, but these are the two parameters you play with to
mm,
produce the torque. Now, if you are having a material where you're reaching the magnetic flux density fast or saturating quickly, you'll have to push more current to get the required output from the motor. And what happens then if you actually push more current? You are actually increasing the losses. Material has saturated already. You're
mm,
pushing more current to get the torque. You're actually increasing the losses. You're increasing the heating, and you're making the motor less efficient.
mm,
So you want to have a material where you're actually reaching the saturation point. Uh, it's located at a higher level.
yeah,
So that's also very important.
mm,
So these are some of the parameters which you look for in an electrical steel or a
yeah,
magnetic material for
mm,
electrical motor core.
yeah. Uh,
Mhm.
then there are some you could call them additive parameters like formability and that you could isolate it because you don't want it to make shortcuts. But if we
Yes.
look at formability, could complex shapes be of interest? I have seen some people who are trying to make complex stators with 3D printing.
Yeah, the additive manufacturing thing.
Hmm.
Yeah, I haven't explored that. I mean, I know it's a thing, but I haven't explored that much. But if we're
Mm.
talking about the isolation part, uh, or maybe I can just show you this slide. So when you
Mm.
laminate,
Yeah.
you want to have some kind of insulating layer in between. You don't
Hmm.
want to, as you said, you don't want to create shorts. So
Yeah.
usually, what I have seen in my experience, the electrical steels I worked with, you have already a coating on the electrical steel,
Yeah.
and when you actually stack them together and press them and heat them up in a oven, the bonding melts, and all the stacks they stick together, and there's also a layer of isolation between them. So
Mm.
that's how you isolate the laminations with some coating on it, which
Yeah.
creates an insulating barrier
Hmm.
between the sheets of the
Yeah.
steel.
Yeah. But in 3D printing, you can add this layer as a so you make a dual deposition
Uh,
with two different materials, the
okay.
isolator and the
Mhm.
and the iron. That's at least
Ah,
what I have
okay.
seen so far.
Okay. Okay.
Uh, mm, uh,
Listen.
if we look deeper into the specific materials,
Mm-hmm.
we have been discussing some potential materials, and typically, if you look at the materials, ferrites are the
Mm-hmm.
cheapest ones.
Yes.
But why are ferrites not used as stators in motors,
Yeah,
or
okay.
are they?
Yeah. Well, that's actually a very good question because what I have seen, they are always used for applications where you have higher frequencies of range 100 kilohertz to 1 megahertz.
Mm,
So like switch mode power supplies, radio transformers, inductors. They do have properties like high magnetic permeability. So we want that in an electrical steel for a motor.
mhm. Yeah.
But I was reading a paper and they actually came up with a value of how low. So the disadvantage of ferrite is it has low saturation flux density compared to an electrical steel. And I think the number was around, it has one-fourth of magnetic
Mm,
flux density reduction
yeah.
compared to electrical steel, according to that paper. But
Hmm.
uh, to tell you, it's actually lower in such lower saturation flux density
Mm,
is the disadvantage of the ferrites. So that's why we don't go for motors in that case. And also, as I mentioned before, we don't want that any material to have that property. So high permeability is good. Lower losses
mm,
at high frequencies is also nice. But then if you have a lower saturation flux density, I don't know. I mean, you can't push much out of that motor. So that's
mm.
why probably they're not very popular with motor cores. There might
It.
be some small motors where you actually don't care about uh, losses at lower frequency so much, or maybe it's
Mm,
reaching saturation flux density. But I'm not aware of those applications. Only the radio frequency applications.
yeah. Yeah. That I think that's pretty fair. I could imagine something where you go to extremely high speed and
Hmm.
you go small, then you have very high frequency, and their standard materials, they have too high losses. Then it could be of interest, but of course you have to add four times the amount of material to get around the saturation level. So the motor will be big, and
Yeah,
going big when going extremely high speed is
not good.
the wrong way.
No. Yeah, I think it's the completely the wrong direction you are
Yeah,
going into for high speed.
yeah.
And also, I think that since I mentioned the range of frequencies around 100 kilohertz to 1 megahertz, talking about that frequency range, I don't think any motor will operate at that frequency. I'm talking about only the fundamental frequency of the motor.
Mm,
So because you always, for a high speed application, you always design for lower number of poles. I don't want to get too much into detail, but I just want to
mm,
put this point that the reason you do that is you want to keep the fundamental frequency of the motor lower at
mm,
that high speed
yeah.
because it has consequences on the inverter. Because if you say my fundamental frequency for the motor is 1 kilohertz, And roughly speaking, what your inverter will be handling, just a rough number, if you multiply that 10 times, so your switches in the inverter is going to switch 10 times that frequency, so 10 kilohertz. Now, the question is, will the inverter be able to handle that losses? So the losses due to switching frequency. So you also have to think about that. So if
Yeah.
you're already thinking about kilohertz range, probably I don't think you will do that for a motor. So that's also, I think, one of the reasons you don't really, you cannot really benefit from this material at lower frequencies. And also, they're not good at lower frequencies
Yeah.
in terms of losses.
Yeah. But if we look into materials that can be used, and then laminates is the big one. And there has been some talking about that laminates, they go thinner and thinner, and I think today it's often 0.15 millimeter when you go to the very thin one. And I'm not sure what size they use in electrical motors for cars, but I think it's one of the thin versions. But can you help me on that?
Yeah, yeah. Actually, I have seen the 0.1 mm also
Hmm.
from Tata Steels. I think it's called NO10.
Hmm.
That's 0.1 mm.
Yeah.
That's the thinnest I have seen,
Yeah.
if I'm not wrong, as
Mm.
far as I remember. So, I mean, of course, thinner the better. But then again, depends on the factors like availability and cost, and what is the minimum, uh, like, how do I say this, minimum production number you want your motors to, or your company should have to get that steel, basically all the logistics and the cost. So thinner the better, because also if you see the data sheets of electrical steel of different grades, of different thicknesses, there is a parameter while we design motor we look at is watts per kg for any electrical steel.
Mm.
Now, how much losses that electrical steel has per kg, and that
Yeah.
should be a lower number. So thinner the grade, better. But then
Hmm.
again, you have to think about the losses and the cost and the availability. Also, when the material gets thinner, also I think the handling part, I think you have to be probably very careful in the tooling and the stacking so that you're
Mm.
not bending it too much or it's not deforming.
Yeah.
So I
Mm.
guess these three factors needs to be considered.
Yeah. Then on the slide you have written it can be grain oriented or non-grain oriented. What does that mean?
So grain oriented, like the electrical steel, you are rolling it in a particular direction, so it has similar magnetic properties in the direction of the rolling, as far
Hmm.
as I understand it. And the
Yeah.
non-grain oriented is having uniform magnetic properties in all the directions, basically.
Okay.
And now the question is, why is this important? Or why do
Mm.
you have these two kinds of electrical steel? So we have two magnetic components. We have on the left, if you see, that's a core of a transformer.
Mm.
Uh, and on the right side, that's the stator core of a motor. Both use laminated electrical steel. Now you can ask me which one goes where. Commonly, you use grain-oriented electrical steel for transformer, and the reason being the flux in the transformer
Mm.
is in a particular direction with respect to the rolling direction. So you have better properties in that direction, and it is better suited for transformers. So you have higher magnetic permeability, lower losses in that direction. But in an
Hmm.
electrical motor, you don't
Yeah.
have a specific direction. It has
Mm.
different directions, magnetic flux.
Yeah.
So you want to have uniform magnetic properties in all the directions you can get. And that's why you use non-grain oriented electrical steel in the second case, which is the motor.
Mm. Yeah.
So that's the reason.
Yeah. Typically, this is made in very fine iron with a little of silicon, so the saturation level is theoretically around 2. But then you add this isolation film on each layer.
Mhm.
Does that take up any space? Does it reduce the saturation level? And then the more layers you have, the thinner you go, the more intermediate layers you must have, meaning that the saturation level of a 0.1 must be smaller than 0.35, or how is it?
When you talk about packing these
Mm,
sheets into a stack, so there's something called stacking factor, and
mhm,
you want that to be high. So if you want to have a rotor core of, I don't know, 10 millimeters, and you say I have X number of, or maybe I need 30 sheets, for
mm,
example, to get that. Now that 30 sheets, you need to calculate taking into consideration the thickness of the electrical steel. Now, the thinner the steel,
mm,
higher the number of sheets you need to have to get
yeah,
that size and a
mm,
higher packing factor. So I think that's you need to have a higher number of sheets if you have a thinner material to get the
mm,
stacking factor required for that core for a given core size. So that is definitely a very important factor to consider when we talk about the saturation level. If we keep this insulating material aside and we just compare, maybe I should have put some electrical steel data sheets here
mm,
between two grades, which is say point 0.1 and the other is point 0.3, for example. Uh, I need to look into that a little bit more in terms of the saturation level, because when you're comparing only electrical steel and you
mm,
take the coating away, I'm not really sure. I need to look that number up, how
yeah,
the saturation affects with the thickness. I think I'll look at it
mm,
later, compare in terms of data sheet.
yeah,
If how does that work?
yeah. Maybe some of our listeners could
Mhm.
tap in and write it in the comments. I would love to learn if it has any effect.
Yes, I think it's a very great point, and I think I should look at it. Yes, I will do that.
Yeah. Then if now we talk about saturation level, there are some people who wants to have the best of the best. The king
Hmm.
of saturation level is the alloy with 49% iron, 49%
Yeah.
cobalt, and 2% vanadium.
Yes.
Yes, that guy. Um,
Yes.
yeah, but what is it for? Can you in my head it looks like a very expensive material, and just to get you get just a few percentage more of saturation. Is it worth it?
Yeah. Yeah. When I was actually looking at this material, I mean, it has cobalt, right? So cobalt is expensive. So this guy
Hmm.
is quite expensive.
Yeah.
So that means this guy is only available for specialized applications. And the other day, I was reading a paper and this graph, and you see the comparison between different grades from different countries and thicknesses and typical
Mm.
losses, and you can see the saturation levels as well.
Yeah.
Uh, Definitely, it saturates at a very high B. So that the paper, this is from that paper, and the material which they were using was IJ22 alloy, which is a Chinese grade, and it's a iron-cobalt-vanadium grade.
Mm.
You see the saturation level is around 2, so it saturates quite higher as compared to the other grades.
Yeah.
And the application involves power dense motors for aerospace applications, marine applications, racing cars, I think also,
Hmm. Yeah.
because you want to have those motors to be very power dense and should have very high magnetic saturation flux density, so higher magnetic loading.
Yeah.
So those are the specialized applications, and I think for those applications, it makes sense to use very specialized grades. If you, for example, talk about aerospace applications,
Mm.
but for applications like I don't know, maybe flywheel, probably I'll not use that because it's quite expensive, and
Yeah.
I need to
Yeah.
think twice about that. Also, like when you're selecting grades like 0.1 mm or 0.3 mm, we think a lot about cost in those two
Hmm.
between those two grades as well. So definitely, maybe the iron cobalt vanadium is not a very what is attractive option in that case for simple applications. But
Yeah.
specialized, yeah,
Hmm.
definitely. We have to think about a lot of things there. And there's a European company, Vacuum Schmelze, which they make also FeCOV grade electrical steel. They're called FLux
Yeah.
48, and they say they have saturation polarization of around 2.3. And
Mm.
the applications they mention here is aviation, spacecraft application, motor racing. So
Yeah.
very specialized application.
Hmm. Yeah. Uh, but how is it made in sheets as well, or how is this produced?
I'm not very sure about the production of it, but I think it's also like electrical steel sheets, I
Hmm.
believe. If I can find some information. Yeah, strip material thickness,
Yeah.
forms of supply. So 0.05 to 1 mm, that's what the data sheet says,
Hmm.
with 120 to 280 mm. So yeah,
Yeah.
electrical steel sheets of
Yeah.
iron-cobalt-vanadium.
Mm. Yeah. So it's same manufacturing method as the standard silicon laminated alloyed steel.
I would actually say yes, with a pinch of salt, because again, you have
Mm.
cobalt and vanadium added to the alloy,
Mm.
but electrical steel has silicon. So I don't know metallurgically how these additions may have different ways of producing them. But if they are made into sheets, yeah, simplistically talking from a motor designer point of view, I would say, yeah, okay, they probably have the same way of
Yeah.
manufacturing. But
Mm.
chemically, I'm not sure how they are done because of these different materials they are
Mm.
added to
Mm.
the main alloy.
Yeah.
So I
Uh,
might need to check that
yeah.
also.
Mm. Uh, and that leads us to the soft magnetic composite material.
Mm.
Um, and SMC, as they are also known, are made in a very different way. Um, it's a powder-based material, and uh, I would like to give some insight in what that is, because I'm working with that on daily basis. And when you showed that in your laminating you have isolation layer by layer, when you work with powder, every single powder grain is around 100 micron, so zero point 0.1 millimeter. But then every single grain is coated with an isolation, meaning that when you put them together and you press it into a shape, then you do not have isolation layer by layer, but you have isolation in 3D. So
Okay.
it is similar to the material you said that did not different have different properties in different dimension. It is really homogeneous,
Mm.
isotropic in its properties. And then it is pressed, and when you press
Mhm.
it, you deform it. And
Mm.
when you deform iron, you introduce stresses. And these stresses, they give higher hysteresis losses,
Mm.
because that is, when you introduce stresses, is also called strain hardening.
Mm.
And hardening of material is the same as hardening hard magnets. They are also hard. They are very
Mhm.
brittle. So when you introduce hardness to the material, you also increase the coercivity. So you have higher
Mm.
losses.
Mm.
So therefore, after compacting and shaping the geometry of the part, we need to heat treat it. Uh, and the perfect world, it would be possible to heat treat it at a temperature where it's fully stress annealed. And then we're down to zero in pre-stresses. But unfortunately, when you have such a high surface area with all these small grains, if you go to a temperature where you fully stress anneal it, the activity of these surfaces is so high that you start to cinder. So they start to grow
Mm.
together and make shortcuts. And then we come back to the picture you had with a block. instead of your isolation. So if you go to too high temperature, you break down this isolation. So therefore, there's a trade-off in the production of SMC where we heat treat it to the temperature just below sintering starts to avoid the shortcut formation, but to stress relieve it as much as possible. So that's the manufacturing method. But then why could SMC be an advantage? And I'll just share. I made a block about some years ago on it, and here we are not talking material properties. We're more talking design. And if we take a standard stator tooth. I call the outer the yoke, the place where you have the winding, I call that the bridge, and then the tooth on the inside where the rotor rotates. And when you're working with SMC, you are able to make different heights. When you make laminating, you have laminate by laminate, so you have uniform height all over the piece. But when working with powder, we can make the yoke high, we can make the bridge small, and we can make the tooth high. And that results in a motor that looks like this. Meaning that when you have it standard height with laminating, you have your end winding. The winding goes above the height of the stator. But if you can reduce it, you can put the winding inside the height of the yoke. This means that your winding is shorter. And when we talk about losses in a motor, we have an example here where we made calculations of losses. You can see when going from a laminate to the SMC, the iron losses, they more than double. But due to the lower amount of copper, then you can see the copper losses, they are reduced linearly with the amount of copper you save. And if you sum these up, the total loss in the stator is far below by taking this design. So SMC is not necessarily a smart material, but it's a material that enables smart design. That's how I would put it. And in this case, of course, you can only do this if you are below saturation level in your bridge. Because if you have designed your motor to be fully saturated all over, then when you reduce the height of the bridge, exactly as you said when we talk ferrites, if you go over saturation level, then you will have higher losses. So this is a trick you can only do if you are below saturation level. But I have seen a lot of motors being designed like this that can be reshaped into this morphology.
Okay. Nice.
Yeah. So that was my lesson on SMC.
I'm so happy to hear that from you, Peter, because whenever I used to read about SMCs, I mean, I have only seen them used in axial flux designs and not very commonly used in radial flux design. And then the question comes like, if it's so promising in terms of losses, reduction in eddy current losses, to be very precise, the SMC has lower eddy current loss reduction, whatever I've read so far, and higher hysteresis losses, as you mentioned, because of the process. I always used to think like, then how is the core loss lower? Because you're actually increasing the hysteresis losses. How is it advantageous to you? And then this block says it all, like, okay, you also have an effect on copper losses because the way you design that very tight windings, so you don't have that hanging end turns, which is basically a lossy material and do nothing to your motor, just creating heat, which is very important. And also the freedom, I think, in SMC to work with the SMC. You have the other day I was reading somebody comparing SMC and electrical steel to a cookie batter. So when you have an electrical steel, you actually cut the cookie with a cookie cutter. So you have
Yeah.
very restricted
Hmm.
shapes you can
Yeah.
achieve with
Hmm.
electrical steel.
Yeah.
But if you want to have an SMC core, for example, you can spread the batter the way you want and mold things
Mm.
out of it, whatever
Yeah.
shape of cookie you want. In this
Yeah.
case,
That's
motor
right.
core.
Yeah.
So I think you have a lot of freedom, and I think in axial flux designs you need that. So that's
Mm.
why probably they're very popular. And the other thing I was thinking in terms of lower saturation flux density. So SMCs have a lower saturation flux density compared
Mm.
to electrical steel. And then the thinking I had, like, why do they use that in axial flux and not in radial flux?
Yeah.
But axial flux, the way they work, probably adds to the disadvantage of, or
Mm.
kind of
Yeah.
balances this disadvantage of lower
Yeah.
saturation flux density.
Mm.
That's what I think.
Yeah. But I think saturation level is when you stack the laminate. Well, the question I had before with the isolation in between, you typically can reach saturation level of your final stator around 1.9.
Mm.
And with the SMC, we reach typically saturation level 1.7 to 1.8. So the difference is not that big,
Mhm.
but very often people they compare with fully saturated pure
Yeah.
iron block,
Mm.
where you can go above 2.05
Yeah.
or something like that. But
Yeah. Yeah.
uh, I think you, to be fair, you should compare it with the properties of
Yeah.
the not the material, but the system.
Yeah. Yeah. Like the stack, for example, like a core made in
Yes.
electrical steel and a core made in
Mm.
SMC, and then
Yeah.
look at the saturation levels for both.
Mm.
Yeah, I
Yeah.
think that's a
Yeah.
fair comparison.
Mm. But the rule of thumb, never design a motor with SMC the way you would design it with the laminate, because then, as you say, the losses, especially when going at lower frequencies,
Yeah.
are higher on the SMC due to these remaining stresses we still have. So
Mhm.
the at DC we have higher losses, and they only go. I think you have to go above 150, 200 hertz before they equal out with the
Mm.
laminated losses. Um, so
Okay.
there are some potentials, but
Yeah.
always add a design to it if you want
Mhm.
to go SMC.
Yeah. Yeah.
Um, Then I think we should also talk about maybe the future boy in the class in materials is the amorphous.
Mm.
Uh, are you experienced with amorphous materials in building stators?
I will say I have 10 minutes of experience from your Amorphous podcast, the one you mentioned in LinkedIn. So I got to understand at least the lattice structure, how it affects the magnetic properties.
Mm.
And then I found some application to it done by Hitachi, which is Troterial now. They did
Yeah.
actually build a motor, and I think it was an axial flux motor.
Mhm.
They did, I think, in 2018, I guess, something like that. So they have a white paper
Yeah.
describing the
Mm.
motor and the specification. I have just one slide, so maybe I can present after you give a little bit of overview and your perspective on it, so I can just pull up afterwards the slide.
Yeah, I really think it's interesting because
Mm.
if we just go back 20 years, uh, it was very difficult to make amorphous iron-based materials. Uh, but adding some alloying elements to it, typically lowering the melting point and changing the viscosity. Because the
Mm.
reason why it can stay amorphous is that when you have the metal in liquid phase, uh, when it solidifies, if the liquid is very viscous, then you can easily move around with
Mm.
your atoms. And place them into the structure network, that is the crystal network. But if the viscosity is high, like an oil, it's difficult to get into place, and then it solidifies like that, and it was stuck there out in the middle of where the lattice structure should have been. And that is the definition of amorphous material, that it never came to the position where it's in a lattice structure. Because it's not in lattice structure, you typically, with standard metals, you can conduct power through or have electrons run, because the electrons can run in the lattice structure. So that is the reason why metals has a high conductivity. But as we do not have these lattice structures, electrons, they have to run like that. And therefore, conductivity is often a lot lower, or resistivity is a lot higher. And we talk typically resistivity that can be 3 to 5 times higher than you see in standard iron-based materials. So that is one reason why it's good for a sheet, because you still have the iron, and you still have almost the same density. And that means that you have the same saturation level, but you have a higher resistivity, so you can avoid the eddy currents, but you can have your high permeability. The difficult part is that it is still difficult to make in bulk. And when we talk bulk, it's thicker parts. So you cannot make a block of it. You can only make it in ribbons. So typically it's made, you have a melt, you pour the melt on a spinning wheel, and from that wheel you produce, or on the wheel you solidify extremely fast, you create a ribbon, and you pull it out, and you can make a continuous casted ribbon that you pull out. So you can have it, and you can roll it on a coil. Compared to before, when we talked hardness, the amorphous material are typically very hard, very elastic, so you can make them jump. And here it looks different, because normally when we talk soft magnetic and hard magnetic, they should not be hard if you want low losses. But here it doesn't matter. So it's very strange. So this means that you can produce these ribbons, and you can stack them exactly as you do with the laminated sheets. But due to the even lower losses, because you cannot have the eddy current run in the layer either, then you have even lower losses. So this is for extreme low loss machines.
Okay, I see.
Yeah.
Okay.
And another advantage that I really like is that due to that you don't have these lattice structures, you don't have what is called magnetostriction. Many materials, if you put a magnetic field on it, it can change dimensions. And this change in dimension with magnetic field change is noise. So often you can hear a motor. It makes a humming, a summing. But as these materials, they are not affected mechanically or dimensionally from magnetic field, then they don't make noise.
Okay.
So if you want a very low zero noise motor, this is the material you should go for.
Okay.
Saturation level is a little lower. It's not 2, Tesla, it's around 1.55. So
Okay.
you have to be aware of that when you design it, not to
Mm.
oversaturate it.
Mm-hmm.
Mhm.
Yeah,
So
that
that
was
was the story
yeah.
of these materials used for soft magnetic applications.
Thank you so much, Peter. Like I got to know so much about Amorphous, and
Mm.
I don't know if I have time. Maybe I could just quickly show that slide I was talking about,
Mhm.
where I
Yeah.
actually put the yes. So actually, this was what the Hitachi Metal Limited had actually in their white paper. So they build a axial flux motor of 200 volt.
Wait a moment. On my screen, I see the iron-cobalt-vanadium material.
So this is actually the I have also have a reference here for the audiences if they want to visit this white paper and read more about this. So this is the motor they built, an
Hmm.
axial flux motor out of amorphous material, and they have a patent on how to make. I think they have a patent on how they make the core out of the amorphous material, and they have this material med glass which they have used in the core
Yeah.
2605 SA1.
Mm.
So yeah, that's what actually I found, and yeah, I was also reading that it's quite difficult to make the cores out of amorphous,
Yeah.
according to
Mm.
my research.
Yeah.
But yeah,
You
that was all.
you really need some special applications.
Yes,
Yeah.
yes.
Ruchika, I have maybe two more materials.
Mm-hmm.
The iron silicon and the iron phosphorus materials. And we talked about they are not very used in motors, and we have an idea that they might be more used into DC applications. Is that also your feeling?
The phosphorus alloy, if
Mm.
you are mentioning, maybe I also think that, but I really need to understand what is phosphorus doing to that material
Mm.
basically, and then basically start thinking about the application and how
Yeah.
it's applicable to DC or if it has limitations for
Mm.
AC. Yes, so I need more
Yeah.
information on that one.
Yeah. I think what is happening when you add phosphorus do not like to be a part of the grains. So the phosphorus goes to the grain boundaries and make an iron phosphorus phase.
Mhm.
And this iron phosphorus phase has a low conductivity, meaning that it isolates the
Yeah,
grains. So the conductivity of the material is reduced. So
okay.
kind of like you do with your laminate,
Yeah.
but here you incorporate it into the material. So I think that is the purpose
Mm.
of it. But I would love if some of the listener are experts in these materials and are producing them. Please write your comment and let us know if you have some applications for it where it's used. I would love to learn about it.
That would be
Uh,
nice.
yeah. So let's jump to the other part of the stator, the winding itself.
Yes.
Uh, Copper is the working horse here.
Mm-hmm.
Um, what is important about the copper?
It has I would say it has lower resistance as compared to aluminium.
Hmm.
So we are talking about lower losses here, I square R
Yeah.
losses.
Hmm.
And I think, when we talk about winding losses, we always refer to them as copper losses.
Yeah.
But what do you say when you have aluminium windings? Aluminium losses?
Yeah.
Because traditionally people have always used copper. So
Yeah.
they always say copper losses, meaning
Hmm.
winding losses.
Hmm.
But basically they are I square R losses. So you want to have a lower resistance. Also at normal temperature, also at higher temperatures, because
Hmm.
resistance goes up with temperature. So you also have to think about the resistance at higher temperatures. So copper has a
Hmm.
lower resistance, so offers lower copper losses.
Yeah.
winding losses.
Mm.
Aluminium, on the other hand, has a higher resistance as compared to copper. So they are more lossy, but still they are used in applications where you need to have lighter designs, and
Mm.
they are cheaper than copper. So
Yeah.
aluminium is
Mm.
used. But you know, everything comes with advantages and disadvantages. If copper is cheaper, lighter, it has higher losses, it has connectivity issues, and connectivity issues meaning the soldering of aluminium is
Mm.
difficult.
Yeah. Yeah.
Why is that? Mm.
I heard, I don't know if it's just a story, but I heard that in the 80s, many houses were built not with copper wire in the electrical connection, but with aluminium wires. But due to the difficulties in connecting it at the end, you could easily put it in the walls, but when you have to connect it at each end, uh, it was not very good. So they were the reason for some fires,
Mhm.
and therefore
Mm.
insurance companies wanted to avoid it.
Mm.
But how is it today? Is it still a problem soldering or making mechanical connections when you need to connect it at the end of the wire?
Yeah, I mean, the problem comes from they create a oxidation layer, which is very difficult to break when you want to
Mm.
solder it.
Yeah.
So there are special soldering elements or materials to solder aluminum wires these
Mm.
days, as I was reading about them. There are special techniques too, and I actually have three of them to tell. Here, high pressure crimping is one of them. So you crimp basically the wires, the aluminum wires, using a high pressure, not heat, but
Hmm.
just a high pressure. So make like a gas tight joint,
Aha.
and that helps. But it has a disadvantage of mechanical stresses. So that's the disadvantage. Then there is another one which is ultrasonic welding, and this ultrasonic vibrations creates heat, which
Hmm.
penetrates the oxidation layer, and then you can make a connection. But then you
Aha.
need the specialized ultrasonic equipments to do that. Not
Mm.
good for small motors and where you want to have a, you know, competitive compact product.
Mm. Hmm.
You need to think about some smart ways to do it. And then
Yeah.
the last one I actually listed was aluminum to copper transition joints. So you have a terminal which creates copper and aluminum. I don't know how that practically works, but I assume that you have a joint and then you have a one end copper connecting to one end and aluminum connecting to one end, and you
Mm-hmm.
solder the copper part onto the PCB, for example, or
Mm.
onto the other connections where you want to make with the power cables, and that's how
Yeah.
you basically make a connection.
Mm.
The disadvantage for that one was think don't remember, but I don't know if they're very easily available, those kind of connection
I
joints.
could imagine the last one is double. You have to make two connections
Yeah, a lot
for
of
each.
work.
So
Yeah, yeah,
price will of course be double.
yeah, that could be, yes.
Mm.
These are the three I actually looked into, and also I had some experience working with aluminum windings in one of the designs. And the supplier inputs I got was the connectivity issues. And then when you want to wind the windings, you need to
Mm.
stretch the material, and aluminum is not very strong as compared to copper. So they asked me like, what's your motivation to go for aluminum windings, or why are you even looking into them?
Yeah.
So that's actually what the supplier input
Mm.
I
Yeah.
got. So that's also
Mm.
one of the issues.
Yeah. I could add some other arguments why it could be smart, especially these days where majority of copper is mined in South America. Uh, in Europe, we don't have copper mines, meaning
Mm.
that it's a strategic material because we are so depending on it in our electrification. So therefore, it could be a way of reducing our dependency of other areas. So if we look globally and strategically, and then of course weight is a major part of it. I don't know about isolation. If you do you need it with copper? You typically put a thin layer of lacquer isolation on it. But I could imagine that the aluminium wire itself creates an aluminium oxide that could be the isolator, so you could avoid this lacquer.
But they create probably those at the joint. So where you connect the winding ends to, for example, power cables. But if you were talking about isolation in terms of winding isolation, copper is more lossy, so it produces a lot of losses as compared to copper. Aluminium produces a lot of losses. So of course you need a higher grade isolation material for the windings, and also to produce or to run the same amount of current what you would run in a copper winding or copper wire, you need more aluminium in case of copper. So that also needs to be
you need to make it thicker.
Yeah, you need to make it thicker. So you need to also think about the space in the slot. Do you have enough space or not? Yeah. So these reasons are also important.
Yeah, it's not just exchange it 1-to-1.
No.
Yeah. But if weight is important, then if we take it 1-to-1, density is a third. So you can really reduce weight. But then, as you say, of course, you need to add more copper or more aluminium and make them thicker. So that might eat up some of the percentage back again.
Yeah. A lot of optimization to be done there.
Yeah. Then if we look at motor designs, I mentioned some of it during the SMC, but a lot of people, they are only seeing motors as radial designed. It could be an inner runner or an outer runner, but that is is it 99% of all motors? They are made like that. But then the axial flux motor has been on the market for some years, but why is that an advantage, or why is it a disadvantage to go axial flux? I have seen it in some of the motors built for very high power density cars, like the Koenigsegg. When they went electrical, they told that we are going electrical, but the car can still smoke, and then they made a donut.
Yeah. I remember that. Yeah. Axial flux motors are quite old. They're not new, but they are gaining actually popularity recently a lot. And there's so many companies actually working on that design. But I was, in my opinion, why it was not popular because of probably the production issues, like the tooling, for example. That has to be very different to build those kind of motor cores, for example, or wind them. So that's why probably they were not very popular. But I think due to the advancements these days, they are gaining popularity as the tooling is also improving, I believe. And then you have SMCs you can use in axial flux machines and mold the cores the way you want. So I think we will see a lot of development in axial flux designs. But I think there was also an article, I don't remember from which company, they were comparing radial flux and axial flux, and they were actually trying to, I didn't read it completely, but why you shouldn't neglect radial flux while looking at axial flux. So basically, both have their places and how they play their parts in this the application today. So I think I'll find that paper out and try to link it if I can. But definitely, axial flux is gaining a lot of popularity, and I think it is something to watch out for. I think, and I think I should also start working a little bit on that.
Yeah, I fully agree. Yeah, yeah. I have seen some saying that they could deliver 10 kilowatt per kilo motor only based on air cooling, and I have seen up to 40 kilowatt per kilo motor with forced liquid cooling in axial flux motors.
Okay. Well,
So it's a very high power density.
Yeah. I mean, this company, UK company, YASA, which makes axial flux, and they recently had an unofficial world record of efficiency with their axial motor. So, yeah, I mean, they're doing some great things in that field. So definitely to look out for.
Yeah, I agree. Ruchika, I don't have more questions on my list. Do you have a final remark you would like to add to our conversation today?
Yeah, actually, I just want to show a last slide with a small message I have.
Yeah.
I will show it quickly. And let me know if you can see my screen. Can you?
No.
Okay.
Right now it's yeah.
Okay, I think now you can see, right?
Yeah. It's the presentation from
This was the motor I was talking about from YASA. So they have this axial flux and radial flux, and actually just see the size comparison. Like with axial flux, it's so lean, like a pancake, and then you have a radial flux. So you have a approximately 1/3 reduction. I think that's the motor. Yeah, so yeah, they're getting quite popular. And my last remark would be I actually recently published an issue about materials in my newsletter, and I'm picking that up from the issue itself. So materials are actually the biggest part. I realized while I was designing motors that you just simply cannot pick anything up after you finish the design and say, okay, my motor is ready. And it has to be a well balance between the design and the material. And when people say, what's the best material for your motor? It's not the best. It's whatever works best for that application is the best material for your motor, in my thinking. So that was my thought in the end about the material selection for motors.
Wonderful. Thank you very much. I really enjoyed our conversation, and I hope that people will start following your blog on Mind Your Motor and learn more about how motors are built.
I hope so too. I'll try my best to present good issues every month. And of course, I'm open to suggestion and feedback from everyone. So please do that if you have any.
Perfect. Thank you very much.
Thank you very much, Peter. It was nice to have you. Thank you. Have a nice evening.